Section 1.2 is all about graphing. We're going to take a look at functions and non-functions, and we're going to look at some of the properties and techniques that we use. Now, the first technique we're going to take a look at is how to graph a point or how to read a point off of a graph. So, starting off, a function f is in the xy plane, and then we have our output, which we typically refer to as y, and that little sub-zero right there means that this is a particular output, like y equals 5 or y equals -2. And we're saying that that particular output corresponds to a particular input labeled x sub 0. Now, typically the way that we find values on a graph and how we graph points in general. So we start with the x value, we move left and right along the x-axis until we get to the x value, and then we move up or down vertically until we get to the y value, and our point is plotted. Now, there's one last thing right here. If we take a look at this last sentence, right here, the intersection is the value y sub 0 equals f of x sub 0. What that's saying is that if you have a point, x sub 0, y sub 0, it is the same thing. If this y sub 0 is on our function, this is going to be on f of x. Okay. If this y sub 0 is on our function, that is the same thing as saying y sub 0 equals the function when you evaluate it at x sub 0. Okay, so with that being said, let's take a look at this first example. And you notice I have some numbers filled in right here already. Let me erase those. And the reason I have to erase those is because I need to remind you, I said this in one of the videos in section 1.1, whenever you work with the graphs in this workbook, always check the scale. So as we take a look at the scale, you notice that there's a 1 and there's a 2 with that mark in between. So the scale is actually 0.5 on the x and the y-axis. So this number right here is a -1. And what I had filled in on my table a while ago was when I looked at it and I thought it was a -2. So starting with the zeros of the function. And if you remember from section 1.1, the zeros of a function is where the function intersects the x-axis. And the zeros of the function are right here and right here. And just to remind you, if the function intersects the x-axis, that is a zero of the function. And when we are on the x-axis, the y value is always 0. Always. So our zeros are at -1 and 1. So these are our x values across the top of the table. At -1, we're going to say the y value is 0, and at 1, the y value is 0. We have another point that we can find fairly easily, but it's important that you move along the x-axis to find these points. And what I'm trying to say here is, as we move from left to right, right here, there's an easy point to find, right there. And that happens at x equals 0. So at x equals 0, we drop down vertically and we hit the graph at -1. So the value of the graph at 0 is -1. Now, the rest of these points are just going to depend on where they hit in those grid lines, about how easy or how difficult they happen to be. So let's start with -2. We go across the x-axis to -2, and then you notice the functions above it. Trace up until you hit the function. It looks like we intersect the function right there, so let's trace it back to the y, and that happened at y equals 3. At x equals 2, all right, that's to the right, so x equals 2 is right here along the x-axis, and then we're going to trace up, and we intersect the function at y equals 1. And at x equals 3, trace across the x-axis, x equals 3. We intersect the function right here, and that corresponds to y equals 2. So we have the points -2, 3, which is the same thing as saying is the y value of 3 is equal to the function evaluated at -2. And we have the point -1, 0, and I'm just pulling it from here. And then we have the point 0, 1, 0, -1. And then we have the point 1, 0, and we have the point 2, 1, x is 2 and y is 1, and the point 3, 2. Okay, so that's reading points off of a graph. And then we had another thing that came up in section 1.1 about our definition of a function, and it was a very nice definition of a function. But basically what it boils down to is as long as the x value does not repeat, then you have a function in this xy plane. Now, we visually inspected some graphs in section 1.1, and we used something called the vertical line test. Now, this is where it's officially defined in the course. Because the x values cannot repeat, and a vertical line will tell you very quickly if your function has any repeating x values. And if you recall from the section 1.1 videos, we talked about that everywhere along a vertical line, in this particular case, this x value all along this line, it takes the x value of -5. So if I graph a point right here, that's the point -5, 4. And then if I move down my vertical line and I graph a point right here, that's the point -5, -4. So the vertical line test works because if you drop a vertical line and it intersects more than one place on your graph, then that means that your x's are repeating. And if your x's are repeating, it's not a function. So here is an illustration. We have x repeating. It fails the vertical line test. So since the x is repeating, it's not a function. Likewise, let me grab a different color. If I drop a vertical line right here, which looks like that is the x value of maybe 1/2. That's the x value of 1/2. That's what I'm going to call it. Looking at my scale of 0, 1, negative, 0, -1, -2, -3, -4. So I dropped a vertical line at x equals -1/2, and it intersects the function multiple times. And since the x's are repeating, this is not a function. If I drop a vertical line over here, and your vertical line can be anywhere. You have your pick of vertical lines. See if I can follow the grid a little bit better. You can see just by visual inspection that that vertical line intersects multiple times along this spiral, and that looks like that's the vertical line x equals 1. And then we move to these functions, or these graphs, down here. And I know it looks maybe like this is going vertical right here, but if you take a look at your graph closely, you can see how that curve is expanding out just a little bit off of that grid line on either side. So if you drop a vertical line anywhere on this function, and I'm going to pick an easy one right there. Well, pretend that's vertical. It only intersects the function once, and so I could drop another vertical line, and it only intersects the function once. And even if I dropped a vertical line right here, pretend that's vertical. Once again, my drawing's not too straight. It only intersects the function once. So since it only intersects the function once, we say this thing passes the vertical line test, and it is a function. So we go to this one. This is even more clear cut. You can drop a vertical line anywhere you like along this function. And every time you drop that vertical line, you only intersect the function once. So it passes the vertical line test. And sometimes vertical line test is abbreviated to the VLT. It passes that. So this is a function. Then over here, we have this beautiful polar graph, and we drop a vertical line and it intersected twice. I just want to point out, if I had dropped a vertical line right here, it only intersected once, and that's really nice. That's great. But the key to the vertical line test is if you arbitrarily just drop a point on a vertical line anywhere, if you intersect the graph twice, as you drop those vertical lines, or more than once, I should say, if you intersect more than once, then you do not have a function. So since we intersect this graph twice with that vertical line, we say that this graph is not a function. Now, there was something else we had to do. We had to determine the domain and range of these different figures. This one is a wash, just because there's not a scale on here, so I really can't tell you what the domain and range is without knowing something about polar graphs. But let's go take a look at this one over here, part B. This is not a function, it's a relation. There is a rule that assigns y values for all the x values. It just happens that the x values are repeating. But we can, since it's a relation, we can still find the domain. As we take a look at this domain, it looks like, moving along the x-axis, that's the domain, it looks like this graph is between -1 and 1. So the domain looks like hard bracket because the -1 and the 1 is included. The domain looks like it's all the values along the x-axis between -1 and 1. And then the range, it looks like this graph is still going. I know I drew a little dot right there. It excluded my arrow. It looks like this graph is still going all along the y-axis, and the range represents the y values. So the range of this graph is all real numbers, or -infinity to infinity. This one, as we take a look at it, I know quite a bit about these. You may know some if you've had some classes that deal with spirals. If not, let me just say that this spiral can keep growing. And since it can keep growing, that means that the domain is all real numbers and the range is all real numbers. Okay, so this lovely fellow right here, once again, I need to, let me erase all this, or at least erase these two. This lovely fellow right here, if you remember any from your previous math classes, you just look at it, you're like, oh yeah, I see that. But if you don't, let me just say that this part of the graph is just going to keep going out larger and larger and larger. And eventually, as you get really, really far out from the graph, you will have covered all of the x-axis, all of the x values, and you will have covered all of the y values. This is what we call as a nice polynomial graph. And polynomial graphs have the property of their domain is all real numbers, so -infinity to infinity, and their range is all real numbers. This one right here, we have this graph. We can take a look at it. The domain is all real numbers. And the range of this one, we can clearly see that the range of this graph, let me erase that line so we can see a little bit more clearly. It has a minimum where it's moving down from left to right, moving down the plane, and then right here it turns, starts moving back up the plane. And that minimum looks like it occurs right here, which, looking at our scale, occurs when x is -1 and y is -1. All right, so at y equals -1, if we look to the right of it, it's going up. If we look to the left of it, it's going up. So we say that the range of this function is from -1 inclusive, these are y values, to infinity. So once again, when you do range, you go up the y-axis and you look and see what's going on. That's the range. That's how you figure it out. When you do domain, you move along the x-axis. And along the x-axis, we have all these negative x values that match up to that graph. I can trace up to the graph. And then as we go this way, we have all the positive x values that are covered on that graph. All right, so once again, this lovely polar function, part F, we really can't find the domain and range on that because the scale is not given to us. So we're just going to leave him alone and say we cannot find his domain and range.